In this video, we are going to solve example on properties of Fourier transform. So let us have a simple example. X of t is given as d by dt of e raised to minus at u of t convolving with t into e raised to minus at u of t. So we are supposed to find out Fourier transform of this given example. So if you look at this equation, we have e raised to minus at u of t, e raised to minus at u of t in both the parts. So we have the standard equation e raised to minus at u of t has Fourier transform 1 upon a plus j omega. So using this equation we can simply find out Fourier transform of e raised to minus at u of t. Now in this equation we have the convolution term also, and this e raised to minus at has time differentiation. So use time differentiation property. So property says that d by dt of x of t will have Fourier transform as j omega into x of omega. So if we use this in the given expression, we get d by dt of e raised to minus at u of t as, so Fourier transform of e raised to minus at u of t is 1 upon a plus j omega. So it will be as it is 1 upon a plus j omega. But due to this d by dt, we need to multiply this x of omega with j omega term. So we have obtained the Fourier transform of the first part d by dt of e raised to minus at u of t. Now in the second part we have t into e raised to minus at u of t. So it is this, here we have to use a property frequency differentiation. So this property says that if we have t into x of t, in this case we get the frequency domain representation as j into d by d omega of x of omega. So now in this case, if you look at the second equation, we have t into e raised to minus at u of t. It will have Fourier transform pair with d by d of j omega, j will be as it is, into x of j omega is 1 upon a plus j omega. So if we simplify it, we get t into e raised to minus at u of t, its Fourier transform will be j as it is. Now d by d of j omega 1 upon a plus j omega. So here this integration is simply with respect to omega, not j omega. So it will be now d by d omega of 1 upon a plus j omega will be minus of 1 upon a plus j omega square, and the coefficient of omega is j, so it will be now j square. So ultimately our answer will be t e raised to minus at u of t will result into j square is minus 1, so minus minus becomes plus and we get the answer simply as 1 upon a plus j omega square. So now we have obtained the Fourier transform of these two expressions, but now these two equations or these two examples are convolved with each other. So we have to make use of convolution property. So this property states that if we convolve two signals in time domain, these signals are multiplied in frequency domain. So if you take these two examples, these two examples are convolved with each other, so we get the answer as d by dt of e raised to minus at u of t convolving with t into e raised to minus at u of t will have Fourier transform pair with, so for the first term we have answer as j omega into 1 upon a plus j omega. Here it is convolution, so now here it will be multiplication with the second term 1 upon a plus j omega square. So if you simplify it further, we get the answer as convolving with t e raised to minus at u of t, its Fourier will be, so at numerator we will have j omega and at denominator we have a plus j omega cube. So this will be the final answer for this particular example. So this is the first example based on the property of Fourier transform. So let us see one more example based on duality property, which is very important property. So we have the duality property. So let us take second example. Let x of t is equal to 1 and we are supposed to find out Fourier transform of 1. So see how we are going to approach with this example. So here we need to use duality property. So this duality property states that if we have x of t and its Fourier transform is x of omega, and now if we try to find out Fourier transform of capital X of t, it means from the above right hand side part, here we are replacing omega with t and we are taking it in the time domain. Then its Fourier transform will be 2 pi small x of minus omega. So in this case, this x will be shifted towards right and we have to replace t with minus omega. So we have to make use of this property in this example. So we have delta t, that is impulse function, its Fourier transform is 1. Now we need to bring this 1 towards left hand side and replace omega by t. So here in the right hand side we do not have omega, so straight away we can bring it towards left hand side. So it will become x of t is equal to 1. Now for this equation we have right hand side as 2 pi x of minus omega, so which will be equal to 2 pi. Now our x is nothing but the delta function, so delta of minus omega. But as we know, impulse function is symmetric, so the Fourier transform of 1 is simply 2 pi delta of omega. So this is how we can make use of duality property. So let us see one more very popular example based on the duality property. So we need to find out the Fourier transform of sinc function of t. So remember here, to solve this example we are going to make use of duality property. To make use of duality property, we must understand a standard results where if we find out Fourier transform of a rectangular function, we get a sinc function. Okay. So here we are going to make use of duality property. So we have duality property as if it is x of t with Fourier transform as x of omega, then x of t has Fourier transform as 2 pi delta of minus omega. Now to get Fourier transform of sinc function, we have a standard result that a rect of t by tau has Fourier transform as a tau sinc of omega tau upon 2 pi. Now here we have to make arrangement and we have to make this sinc function, we have to bring this sinc function towards left hand side. Now see what we are supposed to do. Here we are supposed to only find out the Fourier transform of sinc t. So here we need to substitute a tau as 1. So before that let us apply this duality property. So using duality property we can write this equation as a tau sinc of, replace omega by t, so t into tau upon 2 pi, and now this will be your x of t and right hand side will be 2 pi. So I need to make change. Here it is not delta, here it is actually x of minus omega. So here 2 pi x of minus omega will be equal to 2 pi into a rect of t will be replaced by minus omega upon 2. So now towards left hand side we need to simplify the term and make it simply sinc of t. So here we have to do certain arrangement. So here we need sinc of t only. To get simply sinc of t, we must replace certain value of tau. So here put tau equal to 2 pi, so that 2 pi will get cancelled out and this sinc function will have only t function. Similarly, if you look at this left hand right hand side, here we have a, this a gets cancelled out with this a. Okay, now tau is equal to 2 pi, so our equation becomes tau sinc of t into 2 pi upon 2 pi has Fourier pair as 2 pi rect of minus omega upon 2 pi. So let us simplify it further now. So this tau is again 2 pi, so we have to replace it with 2 pi. So again both the sides we have 2 pi, so it can be cancelled out. This 2 pi gets cancelled out with this 2 pi, and rect function is our even function. So we get simplified equation as sinc t has Fourier transform pair with rect of, as rect is even, it is symmetric along y-axis, so this negative sign will have no impact on the signal, so it will be simply omega upon 2 pi. So with this we obtain the Fourier transform of sinc in terms of rectangular function in frequency domain. So this is how we can use the different properties to solve examples.